Hi, this is Mark Weitzman, and I'd like to continue with this deep dive. This is video 4. And this is a deep dive. You know what? I think I'm running out of ink here. I'm gonna go to a green color. I hope that's okay. On the chi-squared and students' t-distributions. And the independence of the sample mean and sample variance. And as I've noted, this is adapted from a book on mathematical physics by Matthews and Walker. The solution is mine, but the problem is theirs, problem 14.7. So previously we derived the PDF of the chi-squared, and we showed that the sample mean and sample variance are independent. Now I'd like to go back to a point that I sort of glossed over in the previous video. And so the question, I said, how do we know that there is an orthogonal transformation that maps x, say the whole point x, the vector x equal x1, x2 to xn, to the vector y where y1 is equal to the square root of n x bar. And to show what's going on, since an orthogonal transformation is essentially like a rotation, what we're saying is if we have a vector x and if this is the distance, this is the y1 value, that we can somehow rotate this vector to a vector like this, call this mx, and the projection, let's call this x1, x2. The projection of mx on the x1 axis will be y1 after we do the orthogonal transformation. And it's pretty clear you can do this as long as y1, the length of the value y1 is less than the length of x. So that's what we have to make sure. We have to make sure that y1 is less than or equal to the norm of the vector x, and or y1 squared is less than the norm of the vector x squared. Well, this is just the square root of n x bar squared less than or equal to x1 squared plus x2 squared plus dot 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 xn squared, or this is equal to n x bar squared is less than or equal to x1 squared plus x2 squared plus dot 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 xn squared. And that just says that divide by n here if we divide by n and subtract, that just says that sigma squared, which is equal to the sum over xi squared over n minus x bar squared is greater than or equal to 0. And we know that that's true. So that gives the justification that I can always find an orthogonal transformation whose first component will be the square root of n times x bar. Now, so let's go on to the subject of this video. We want to derive the distributions of x bar, which is defined as the sum 1 over n, say x bar n, and s. I'm not dividing the s, so this is not our s tilde, but it's related to it. Now we know that the sum of, we know since the xi's are iid normal 0 sigma squared, the sum of independent normal random variables is normal itself, and so we know that x bar is going to be normal mean 0 sigma squared over n. We get a 1 over n squared when we take the variance of x bar n, get a 1 over n squared, and then we're going to have n times sigma squared, so that's sigma squared over n. Now, we also established in the previous video that we can write s as being equal to y2 squared plus dot 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 yn squared, where the yi are iid normal 0 comma sigma squared. So s over sigma squared is equal to y2 over sigma squared plus dot 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 yn over sigma squared, and this is just equal to z2 squared plus dot 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 zn squared, where zi is normal 0, 1. So now, if you remember the definition of a chi-squared distribution, it's the sum, chi squared with d degrees of freedom is the sum of d independent standard normal variables. So that shows that s over sigma squared has a distribution of chi squared. Let's make this Sn with n minus 1 degrees of freedom. And so now we've established the distributions for the mean and the sum of the mean squared deviations over sigma squared. Note, in the notes in class, s over sigma squared would be equal to n minus 1 Sn tilde divided by sigma squared. So this is essentially what we've shown here is Cochrane's theorem. Now, I'd like to give a heuristic derivation, because it's not obvious why the mean and the sample are independent. The sample seems to depend on the mean, so it's, by its definition, it's hard to understand how these two are independent. And I want to get a little better understanding of what's going on. So let me start again by writing down the definitions. X bar is equal to the sum 1 over n xi, and s is equal to the sum xi minus x bar squared. Now, this definition over here essentially defines a hyperplane of n minus 1 dimensions, because it's one constraint. So let's imagine where I can only do 3 here, and I'm not even that good at 3. So let's draw a diagram. x1, x2, x3. These are our variables. The hyperplane, if like the hyperplane goes through the axes, something like this, everything on this hyperplane is going to have the same value of x bar. Now, the vector that we used in our previous video, I'll draw this again. We can draw in n dimensions. I'll do it here in 3. Some kind of vector that lies on that hyperplane that has coordinates x bar, x bar, x bar for 3 dimensions. And it's easy to see that. If x1, x2, and x3 are all x bar, we're going to get 1/3 the sum of 3x bar, which is x bar. So this point lies on the hyperplane. And the sample variance is a sphere centered on the hyperplane that has a radius of the square root of this distance. The distance squared is s. So if I draw a sphere, this distance over here is the square root of s. And every point on this sphere will have the value of the s the same. xi minus x bar squared will be equal to s. And the hyperplane will go through this sphere. It will go through this point and will go through the sphere. So let's say this is the hyperplane through here. And if you use your visual things, you have a plane hitting a sphere, so that leaves a circle on the sphere. So in a sense, we're left with the boundary of a 2-dimensional sphere. We start with a 3-dimensional sphere, then we hit it with a plane and we get a 2-dimensional sphere, which is a circle. And on that circle, every point has the same value of s, and on that circle, because it's also hits the hyperplane, they all have the same mean. So let's use those facts. Let's calculate the conditional distribution of s given x bar. This is defined as the joint distribution f of s and x bar at x and x bar divided by f of x bar, x bar. Now, I'm going to leave out constants, and this is essentially proportional to the integral dx1, dx2 up to dxn. So we're integrating over all points in our n-dimensional space, here 3, that satisfy, that have a mean of s, a mean of x bar, and a sample variance of s. But it's constrained. We only integrate on that circle. So we would have like a delta of x bar minus the sum of xi. This is a delta function which enforces that we're on the hyperplane, and we'd also have a delta function that would enforce that were on the sample value, that were on this sphere. And so this would be del S minus the sum xi minus x bar squared. Don't worry if you haven't seen continuous delta functions and everything. It's just a constrained integration. We're only taking the points that are on the hyperplane and intersect the sphere. Okay, so our conditional distribution is proportional to, I'm sorry, that should be over there, this, and what we're integrating is the unconditional density of any point in the plane is just the n independent normal random variable, so it's at 1 over 2 sigma squared x1 squared plus x2 squared dot 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 xn squared. That's that. And then in the denominator, this, we've already established what the distribution of x bar is. So again, leaving out any normalizing factors, e to the minus 1/2 n x bar squared over sigma squared, because the variance is sigma squared over n. Okay. But we know that we can rewrite the way we always do, that S is equal to the sum over I of xi squared minus n x bar squared. This is just our usual, variance is equal to the expected value of x squared minus the expected value of x squared. That's this thing. And so our f becomes the integral. I'm going to pretend I've done the delta functions integrations, and it's just the integral over a sphere. This is big S, not the sample variance. A sphere in n-1 dimensions. Again, think of this. We start off in 3 dimensions. We have a sphere, which is 2 dimensions, gets hit by a plane, which leaves a 1-dimensional circle. But a 1-dimensional circle is actually a sphere in 2 dimensions. So that's why we have ds n-1. And now I have e to the minus 1 over 2 sigma squared. I'll make use of this. I'll get s plus n x bar squared divided by e to the minus 1 over 2 sigma squared n x bar squared. Now on the sphere, everything here has the same value. X bar is fixed because it hits on the, not the sphere, but on the plane that hits the circle. X bar has the same value because on the plane, everywhere on the hyperplane, it's x bar. So this doesn't depend where we're integrating over. And if you notice, the numerator and denominator cancel. So this is equal to the integral over ds n-1 e to the minus 1 over 2 sigma squared times s, where s is this sample variable that we defined. Now, let me just make clear that the surface S is equal to the hyperplane intersect the hypersphere centered at x bar. And this is the hyperplane through the hyperplane where the sum of xi is equal to nx bar. Okay. Now, this volume, we established in the previous video that the boundary of a sphere of dimension n-1 is proportional to the radius to the, let's see, like if n is equal to 3, then this is 2, the surface, and so it's going to be n-2. So in 3 dimensions, we're going to get a circle. So it's just the circumference of a circle is 2 pi r. R here is the square root of the sample variable. So n is 3. So this becomes 1. So this is equal to let me back up a little bit. So if I want to know what f of s given x bar ds, a little increase in the radius, changes our sample value. This is proportional to the volume, which is the square root of s to the n minus 2, e to the minus s over 2 sigma squared, because this has the same value on the reduced hypersphere and hyperplane that we're integrating over. And then the radius, it's going to be d, actually d times the square root of s. I should have said dr here. But this is, the radius is proportional to the square root of s. So this is equal to s to the n minus 2 over 2 e to the minus s over 2 sigma squared, and then s to the minus 1/2, which is equal to s to the n over 2 minus 3/2, because we have minus 1 minus 1/2, e to the minus s over 2 sigma squared. This is the distribution, the sample distribution of s given x bar. It shows it's independent because there's no x bar here. And it's proportional to this. And if you look at this, you'll notice that this is just a chi-squared n minus 1 distribution of s. Remember the formula we had for the chi-squared distribution. You take the degrees of freedom, divide by 2, so that will give me n over 2 minus 1/2, and then you subtract 1, and that gives me the n over 2 minus 3/2, and then it's e to the minus, actually it should be s over sigma squared. The sigma squareds here don't matter because that's part of the proportionality constant, and then e to the minus chi squared over 2, or s over 2 sigma squared. Okay, so I've given a rigorous derivation here from the previous video, and just a heuristic derivation of how it works out. So I'd like to finish this deep dive series with the next video, where I'll derive the distribution for the student's t-distribution. Thank you very much.